Good afternoon. Today we all are here to attend the PhD thesis defense and viva-voce of Barnasree Chanda. Barnasree did her undergraduate from Guwahati University, and then in 2012, and then she completed her postgraduate degree in mechanical engineering from IIT Silchar, and after that in 2015 she joined our department, and since then she is working with us, and we are very much fortunate that today we have Professor Pinaki Prasad Bhattacharya with us to evaluate the thesis and to conduct this viva-voce of this proceeding. He is the Dean and former Head of Material Science and Metallurgical Engineering Department, Indian Institute of Technology, Hyderabad. So I will simply hand over this session to the Chairman of the TSC, Professor G.G. Roy. But nevertheless, before moving to the proceeding, I simply have a small request to everybody. If you have any objection, in case if this whole proceeding may be recorded. Professor Bhattacharya?
Yeah, it is fine with me.
Okay. No Professor G.G. Roy and others?
No, fine. Yes.
Okay.
Fine.
Okay. So let's, hand over to Professor G.G. Roy. Please begin the proceeding.
Very good afternoon, everybody, and especially Professor Bhattacharya, because you are the external, and to all of you. And it is nothing to start with, because Jayanta has already introduced Barnasree, and Barnasree will just present for 45 minutes, okay?
Yes, sir.
And then Professor Dr. Bhattacharya will take over your viva-voce examination. That's all. Okay, you may start.
Okay, thank you, sir. Good afternoon, everyone. Today I will present my defense seminar on the topic phase stability, microstructure evolution, and deformation behavior of cobalt, chromium, iron, nickel, niobium, tantalum, eutectic, high-entropy alloys. So this will be my flow presentation: introduction, literature review, experiment, results and discussion, which is divided into 4 different parts: conclusion, and scope for the future work. High-entropy alloys are defined as alloys containing at least 5 principal elements and having concentration in the range of 5 to 35 atomic percent. And if there are any minor elements, their concentration should be less than 5 atomic percent. On the basis of configuration and entropy, high-entropy alloys are generally defined as having configuration entropy greater than or equals to 1.5 R. Schematic shows how alloy world can be divided on the basis of configuration entropy. Low entropy alloy has configuration entropy less than or equals to 1 R. For example, low alloy steel. Medium entropy alloy has configuration entropy in the range of 1 to 1.5 R. For example, cobalt-based superalloy, nickel-based superalloy, and then high entropy alloy. Basically, the high configuration entropy by lowering the total free energy stabilizes the solid solution phase. Therefore, rather forming expected restrict the formation of expected intermediate phases. There are many important properties, mechanical and functional properties were possessed by high entropy alloys. Some of the excellent properties were possessed by high entropy alloys. Some of them being yield strength versus temperature, as shown in plot. Which here we compare the comparison of high entropy alloy where with conventional superalloy has been made, where we see that high entropy alloy has sustained very high specific yield strength at elevated temperature. Further, the elongation versus tensile strength and the comparison of the high entropy alloys in this red zone with the various types of steel shows that the high entropy alloys has very high excellent values of yield strength with elongation. So this is the chronological development of high entropy alloys. Basically, in 1996, K.H. Wang, for his MS thesis under the guidance of Professor J.W.A. from NTU University, first started working on high entropy alloys. But it is in 2004 when J.W.A. and Professor Brian Cantor for Oxford University and Brunel University first independently published work on high entropy alloy and proposed the concept of high entropy alloy. In 2006, the major core effects were observed. That is the high entropy effect, severe lattice distortion effect, which is due to the presence of various kinds of atom and in their difference in the atomic size. And sluggish diffusion effect due to the presence of various multi-principal elements. The diffusivities in such alloy are expected to be slower. Therefore, kinetically, they restricted the formation of complex phases. In 2008, Professor Zhang and his group from University of Science and Technology, China, propose a phase formation rule for solid solution on the basis of mixing enthalpy, atomic size difference, and mixing entropy. At that time, the maximum the studies mostly were on single phase high entropy alloys. But if we see that single phase BCC although has high yield strength, but at the cost of limited plastic strain. Contrary to this, single phase FCC has a high plasticity, but at the cost of limited yield strength. Therefore, we have concentrated on the eutectic high entropy alloys. With alternate soft and with expecting alternate soft and hard phase, and to tackle the problem of segregation and shrinkage during solidification. The bar diagram shows the A and B shows the high entropy alloy and eutectic high entropy alloy publications with years, where we see that here there is an increase in the research work on high entropy alloys. But compared to overall high entropy alloys, there is very limited work has been done in eutectic high entropy alloys. So based on that, we have formulated our objectives. That is to develop the eutectic high entropy alloys by suction casting and arc melting to predict and assess the formation of phases and phase stability by thermo-physical and electronic parameters, to study the hot deformation behavior, and further to study the mechanism of microstructural modification and laminar instability upon hot deformation, to study the effect of lamellar thickness and alloy addition on the strain rate sensitivity by strain rate jump test and nano indentation, and further to study the deformation behavior. So, two series of alloy has been developed, that is cobalt chromium iron nickel niobium and cobalt chromium iron nickel tantalum, by arc melting, suction casting, forging, and cold rolling. From henceforward, we will denote arc melting ingot as AMI, suction casted rod as SCR. Further, the microstructural characterization and thermal analysis has been done, followed by mechanical characterization. Figure shows the alloy developed in our laboratory, that is the 3 mm dia suction casted rod, 5 mm dia suction casted rod, and the arc melted ingot. Chapter 1: Evolution of microstructural homogeneity and mechanical properties in eutectic high entropy alloy design. So we consider the cobalt chromium iron nickel as component A, and cobalt chromium iron nickel has single FCC phase. And it has been, from literature, it has been observed that the cobalt chromium iron nickel with niobium and tantalum individually forms binary eutectic. Therefore, considering that, we have considered niobium and tantalum as component B. So we developed the pseudo-binary phase diagram, and from that we see that the predicted eutectic composition lies at 12.5 atomic percent and 10.5 atomic percent for niobium and tantalum respectively. But after experimental trial and error, we got the eutectic composition at 11.11 atomic percent for niobium and 9.09 atomic percent for tantalum. Also, the predicted phases are seem to be FCC and Levis phase. So, phase analysis of arc melted ingot and suction casted rod. First, develop alloy series is cobalt chromium iron nickel niobium. Figure A, B, C shows the XRD patterns of alloy developed by different solidification process, and where we see the reflections of the FCC and Levis irrespective of the development process, alloy development process. Also, there is very insignificant difference in the lattice parameter has been observed. So, optical microscopy shows A, B, C, D shows the optical microscopy of the arc melted ingot, where we see the pro-eutectic distribution over a matrix, and at figure at 0.45, 0.55, and 0.65. But at 0.5, there is no any evidence of pro-eutectic has been, or any trace of has been observed. Similar results has been can be seen in case of suction casted rod, where at except 0.5 there are presence of pro-eutectic phases can be seen. Therefore, further we move for scanning electron microscopy analysis, and along with EDS data, we see that the pro-eutectic phases at 0.45 are of FCC type in a eutectic matrix, which is alternate lamellae of the FCC and Levis phase. And at 0.5, an alternate lamellae of Levis and FCC phase can be seen. At 0.55 and 0.65, the dendrites are of Levis type. And the niobium concentration at FCC phase there is very negligible amount of niobium is present as compared to Levis phase, where there is a higher concentration of niobium is present, which is also supported the pseudo-binary phase diagram. The similar results can be seen in suction casted rod, where Therefore, From this, we can conclude that with the addition of niobium, the microstructure varies from hypoeutectic to a fully eutectic and then hypereutectic. The elemental mapping also shows the similar results. That is, at 0.45, the proeutectic phase are lack in niobium, or very little amount of niobium is present, and at hypereutectic, the dendrites are enriched with the niobium. The partition coefficient also shows that higher partition coefficient value of niobium in the Lewis phase region, which is due to the preferential dissolution of niobium, and due to its high melting temperature and large atomic size, atomic radii among all the added elements. As we see in the optical microscopy and scanning electron microscopy, the distribution, different distribution of proeutectic phase in the eutectic matrix. Therefore, we have quantified those parameters, and the microstructural parameters were quantified as volume percent of proeutectic phase. Plot shows the variation of the volume percent of proeutectic phase with the niobium addition. In case of hypereutectic, we have seen that with the addition of niobium, the volume percent of the proeutectic phases has been, that is Lewis phase, has been increases. The secondary dendritic arm spacing has been measured, and with the addition of niobium, the secondary dendritic arm spacing is increasing also. It is lowest in case of the suction casted rod, and suction casted rod, that is with higher cooling rate. The average eutectic lamellar thickness has been measured, and for hypereutectic, it is linearly increasing, and at the fully eutectic microstructure, the average eutectic lamellar thickness is lowest. And for the 3 mm dia suction casted rod, that is with the highest cooling rate, the average eutectic lamellae is the lowest. The DTA plot shows the single endothermic event, which denotes the melting, and the melting temperature is lowest in case of the fully eutectic arc melted ingot. This is the figure A, shows the hardness profile adopted for the measurement of the hardness at a single point, and the figure B shows the hardness profile across x direction for the 3 mm dia suction casted rod, where we see that at the center of the specimen, the hardness is lowest, and the hardness varies in the range of 624 to 660 HP. Figure C shows that the ASIM image of the lamellae variation from the center to the periphery of the arc melted ingot. And when we measure the lamellae thickness, we get a trend. We get a profile which, that is, as we move from the center to the periphery, the average eutectic lamellae thickness decreases. Also, further we measure the viscous hardness across x direction, x0 x direction, and y0 y this direction, where at center we get the lowest average lamellae thickness, and when as the average eutectic lamellae thickness decreases, there is an increase in the hardness. And when we compare the suction casted rod and arc melted ingot, the hardness for the 3 mm dia rod is 10% higher than arc melted ingot. The mechanical properties has been evaluated by room temperature compression test, and at 0.45 with FCC proeutectic phase, the yield strength is lower as compared to other composition. This is because big presence of the higher volume fraction of the FCC phase, soft FCC phase, and as we add the niobium, the Lewis dendrite, the hard Lewis dendrite increases the yield strength, but at the cost of limited strain. Similar observation has been can be seen in case of suction casted rod, and when we compare the yield strength of the suction casted rod and arc melted ingot, there is an improvement in the yield strength can be seen in suction casted rod with the highest cooling rate. Further, the 3-point bend test has been performed, and which showed at different strain rates there is a noticeable ductility can be seen. Another alloy series has been developed, that is the cobalt, chromium, iron, nickel, and tantalum alloy series. And at 0.2, there is a 80 volume percent of the FCC phase can be seen. At 0.4, fully eutectic microstructure can be seen. At 0.5, the dendrites of CO2 TA type Lewis phase. Also, due to the presence of smaller volume percentage of the tantalum, the yield strength is lowest in case of 0.2, and as the Lewis dendrites phases increases, volume fraction increases, the yield strength increases. The fractography shows the ductile interlamellar fracture to brittle translamellar fracture due to the presence of the facets and cracks. We plotted the yield strength versus inverse of the average eutectic lamellae thickness, and where we compare with various binary to high entropy alloys and see that the present high entropy alloy, eutectic high entropy alloy, consists of excellent yield strength with corresponding average eutectic lamellar thickness. So from here we can conclude that we have successfully prepared two series of eutectic high entropy alloys with niobium and tantalum addition. And the microstructure varies from hypoeutectic to eutectic and hypereutectic. Preferential dissolution of niobium due to its high melting temperature and large atomic size radii can be seen. Also, the niobium increases the yield strength. 3 mm suction casted rod are 2 times finer than arc melted ingot and resulting in the increase in the yield strength, and the local hardness increases from the center to periphery as the average eutectic lamellar thickness decreases. So my second chapter is phase stability and phase prediction on the evolution of eutectic in high entropy alloys. The phase prediction and the phase stability has been studied considering the various empirical, thermo-physical and electronic parameters such as mixing entropy, mixing enthalpy, ohm parameter, atomic size difference, valence electron concentration and electronegativity parameter. The mixing entropy of individual phases and the bulk region shows that satisfy the definition of the high entropy alloy, that is 1.5 R. Further, we have plotted the mixing enthalpy versus atomic size difference, and we compare it with the single phase FCC and single phase BCC high entropy alloys, where we see that the eutectic and near eutectic high entropy alloys are stable in the range of -18 to -6, and when the atomic size difference is greater than 3%. Which is quite reasonable because because positive value of mixing enthalpy leads to phase segregation, and more negative, higher negative value of mixing enthalpy leads to the formation of intermetallic phase. Therefore, and moderate negative value may promote the formation of the two-phase eutectic composition. Another important parameter is the valence electron concentration for the phase stability, and we see that, and when we compare it with the BCC and FCC high entropy alloys, we see that in the range of 6 to 8.5, the eutectic and near eutectic high entropy alloys are stable. Another important conclusion can be drawn from this plot is that in the upper limit of the valence electron concentration, all the phases consist of FCC and intermetallic phase, and in this region, the consists of BCC or topologically close pack or the intermetallic phase. Therefore, not only we will get a prior idea of the phases present, but also we may predict the mechanical properties from this plot. The electronegativity versus atomic size difference shows that the eutectic phases are stable when the electronegativity is greater than 5.5%. So, based on our proposed criteria, various researchers has developed new alloys, and some of them are listed in the table. Therefore, further we have predicted the phases and determined the Young's modulus by artificial neural network. The figure shows a general neural network structure where inputs are the thermo-physical and the electronic parameters, and 209 and 140 numbers of data has been collected for the phase prediction and the Young's modulus for the determination of the Young's modulus. Further, the sample data were divided into main database and deployment database, and the main database were further classified into training set, validation set, and the testing set. The multivariate various parameter has been data analysis has been done, and for the phase prediction, and Pearson correlation coefficient has been considered for the to correlate the various parameters for the Young's modulus determination. This is the general structure proposed for the phase prediction and the Young's modulus prediction. Figure 1 shows the single channel output approach, that is SCOA, where single hidden layer is present with the several neural, and figure 2 shows the 4-channel binary output approach, that is FCBOA, with 2 hidden layer and 15 neuron in each layer. Also, we have assigned the value for the phase prediction. Further, we have improvised this value to avoid any overlapping of the values for the phase prediction. So, for the phase prediction, the figure shows that the mean square error, that the training plot for the mean square error for the training has been continuously decreasing, but after a certain point, the validation and the testing has been increases, which shows that after this point, the network is overfitting. Therefore, we considered that this point is the best trained network. And these are the various parameters for the network training. But in FCBOA at epoch 76, we got the best trained network. Further, for the determination of the Young's modulus, we get at 85, we get the best trained network. The regression plot for the main and the deployment dataset datasets are shown in A, B, C, D, where we see that output the output parameters output in y-axis, that is fitted output in the linear fitted output in the y-axis, and the regression and the correlation coefficient in the plot. When we compare with SCOA and FCBOA, we see that the main database has comparable correlation coefficient, but there is an increase in the deployment database in case of FCBOA, and the phase matching accuracy is much higher in case of deployment dataset for the SCBOA. We are considering deployment database because we are comparing this with the real world data. That is deployment database, we are considering that as the real world data. Also, when we measure the feature importance, it is observed that the valence electron concentration and atomic size difference are the most important parameter while predicting the phases. Further, the regression plot for the Young's modulus shows that the very high accuracy of the deployment dataset, that is up to 98%, and the matching accuracy is 96%. So from there, we can conclude that the eutectic and near eutectic phases become stable in the range of -18 to -6 mixing enthalpy, and valence electron in the range of 6 to 8.5, and the atomic size difference is greater than 3%. Two independent tool has been proposed, that is SCOA and FCBOA, which successfully predicted the phases, but the FCBOA shows better accuracy and generalization than SCOA. Also very high accuracy, and the deployment percentage can be seen in case of while predicting the Young's modulus. So my third chapter is the mechanism of microstructure evolution and spheroidization in ultrafine lamellar eutectic upon hot deformation. Figure A and B shows the high temperature compression test for the 0.5 and 0.4 fully eutectic suction casted rod, and the temperature varies from room temperature to 1123 degree Kelvin. 1123 Kelvin. In intermediate temperature, both in the case of niobium and tantalum, the yield strength decreases, also the strain decreases. But at higher temperature, at very high temperature, that is the 1123 and 1120, there is a huge drop in the yield strength. Also, the strain softening can be seen without any hint of fracture, even beyond the 40%. And this is the button-shaped specimen after deform at 11,023 Kelvin. Specific yield strength versus normalized temperature plot shows and we compare it with the refractory high entropy alloys, aluminum-based high entropy alloys, and conventional super alloys. We see that the specific yield strength versus temperature normalized temperature variation is comparable with the conventional super alloys and other alloys. So strain hardening and flow softening behavior. The Holloman's equation, which correlate the flow true stress and true strain under the deformation at constant strain rate and the temperature, shows the variation. Figure A, B, C, D shows the ln sigma versus ln epsilon for the niobium and tantalum for the intermediate and the higher temperature. Very fluctuating arrays of instantaneous slope along the curve shows the dynamic competition between the strain hardening and the dynamic softening. When the ln epsilon increases, there is an increase in the ln sigma up to a certain value. In this region, the strain hardening is the dominating factor, which is due to the dislocation interaction and their multiplication. And as after a certain value, that is after a peak attained, there is a decrease in the ln sigma, which shows that the flow softening is the controlling mechanism, which is more pronounced in case of higher temperature, that is at elevated temperature, in both the cases, niobium and tantalum. The strain hardening exponent shows that the positive value of the strain hardening exponent shows that the strain hardening is the dominating factor in intermediate temperature, while the negative the negative values of strain hardening exponent shows that the flow softening at the elevated temperature dominates the deformation behavior. Further, the strain hardening rate versus true strain of the niobium and tantalum shows that the theta decreases steeply initially, that is after yielding has occurred, and strain hardening becomes steady and attain to near zero. But in case of elevated temperature, it is the strain hardening rate goes to attain very negative value, denoting the strain softening behavior. Thus, strain hardening rate versus the true stress shows a steep decrease in the theta with the true stress up to a plateau has been observed, which is the critical stress, and beyond which the dynamic softening is the dominating factor. Further, the phase and the microstructure upon hot deformation has been studied. Figure A and B shows the XRD pattern of the deformed, that is button-shaped specimen, and compare it with the solidified condition, where we see there is no any presence of new phases can be seen. Further, the deformed specimen shows the presence of migration, termination, coarsening behavior, and the formation of the Fe to Nb type block. And the microstructure upon hot deformation for the tantalum has been shown in figure A, B, C, D, E, F, and figure E and F shows the specimen has been pre-holed for 1 hour. And when we compare the deformation at the center and the periphery, we can see that the deformation is more pronounced at the center than at the periphery. Also, the different coarsening mechanism, that is spheroidization, formation of spheroidization, lamellae breakage, formation of CO2 Ta type block has been observed, and at 1123 Kelvin for 1 hour pre-holding, almost a complete spheroidization can be seen at the center. So based on that, we divided the coarsening mechanisms such as termination migration, cylindrization, edge spheroidization, and boundary splitting. The termination migration occur due to the termination curvature. Therefore, a chemical potential has been observed, and due to which the atoms move from the termination to the adjacent lamellae. Therefore, recession of the termination and the thickening of the lamella. Direct cylindrization occur when the W by cross-sectional aspect ratio W by H is small. Then the atoms near the curvature moves to the due to the capillary action move to the flat surface, and the cylinder deform into cylindrization shape. And further, due to maybe relics instability, it may further deform up into spheroidization. And edge spheroidization occur due to the when the cross-section aspect ratio, that is W by H, is large. Boundary splitting occurs due to the presence of a groove between the two adjacent curvature, and the termination curvature moves the lamellae material away from the groove, and leads to the splitting of the groove and creation of the spheroidization. From this, we can conclude that at intermediate temperature, the strain hardening is dominating, and at higher temperature, the fall of stress occurs, and strain softening can be evident without any hint of fracture beyond the 50%. And various kinds of lamellar instability can be seen after hot deformation, that is termination migration, cylindrization, edge spheroidization, and the boundary splitting. Also, the Koch-Making plot shows that the dynamic recrystallization on the onset of the critical stress and the work hardening behavior is linked with the complex microstructure of the eutectic high-entropy alloys. Superior high temperature instant can be seen when we compare the eutectic high-entropy alloys with the other high-entropy alloys, refractory high-entropy alloys, and the conventional high-entropy alloys. So my fourth chapter is the effect of cold working on the strain rate sensitivity in high entropy lamellar eutectic composites. The strain rate sensitivity and the activation volume has been measured from strain rate jump test under compression. The following formula has been used for the calculating the strain rate sensitivity and the activation volume. So two jumps has been given. First jump is given at 10 to the power minus 5 to 10 to the power minus 4, and second jump is given from 10 to the power minus 4 to 10 to the power minus 3. Figure A and B shows the arc melted ingot specimen for the niobium and tantalum. Figure A, B, C, D on the right hand side shows the suction casted rod in as solidified condition, and the deformed specimen up to 5% and 10%. But the nano indentation experiments has been performed for suction casted rod at 0.5, that is fully eutectic, and for x equals to 0.65 for hyper eutectic suction casted rod. The indentation versus load versus indentation depth plot shows for the S solidified and for cold work at 5%, 10%, and 55% specimen. At a maximum applied load of 100 millinewton. And figure B shows the load versus depth curve for the matrix as well as for the dendrites, for the S solidified specimen, for the 5% deformed specimen, for the 10% deformed specimen, and for the 55% deformed specimen. Further, to evaluate the strain rate and strain rate sensitivity, we have plotted the indentation depth versus indentation time and from there we have plotted and fitted the ln H versus ln strain rate. From there we have evaluated the strain rate sensitivity. The hardness and the variation of the hardness for the cold working has been has been shown in figure D, where we see that as the cold working percentage increases, there is an increase in the hardness. Also, the hardness is highest in case of suction 0.65 suction casted rod dendrites. Figure A and B shows the ACM images of the indentation matrix and the indentation impression on the eutectic matrix. C and D shows the AFM force gradient on the Lewis phase on the eutectic matrix. There is no any presence of crack has been observed in AFM images. The strain rate sensitivity and activation volume. Figure A and B shows the strain rate sensitivity and activation volume with the addition of the alloy, that is with the addition of the niobium and tantalum, and we compared with the suction casted rod and the arc melted ingot. With the alloy addition, there is an increase in the strain rate sensitivity. Further, the strain rate sensitivity is higher in case of suction casted rod than that of the arc melted than that of the arc melted ingot, which is due to the lower value of the average eutectic lamellar thickness in case of suction casted rod, which lowers the dislocation mean free path in case of suction casted rod. And the corresponding strain rate activation volume is decreases for the niobium and tantalum. The M value increases from 0.0074 to 0.0081 and 0.0070 to 0.0082 upon niobium and tantalum addition. Also, the activation volume decreases from 41.8 B cube to 28.7 B cube and 34.5 B cube to 29.7 B cube. The activation volume remains in this range denotes that the deformation mechanism is dislocation mediated. Further, the effect of strain rate sensitivity on the cold working shows that as the cold working percentage increases, there is an increase in the strain rate sensitivity and corresponding activation volume is decreases. The nano indentation results also shows that the cold working percentage increases the strain rate sensitivity and the corresponding activation volume is decreases. The M value increases from 0.0074 to 0.0081 for S solidified suction casted rod, and for deformed 5% 10% specimen from 0.0082 to 0.0084, and corresponding activation volume decreases from 42.7 to 42.2 B cube and 29.4 B cube to 28.9 B cube for 0.5 suction casted rod, and for 0.65 24.4 B cube to 24.2 B cube. So, scanning electron microscopy shows of the deformed sample shows the presence of steps and the lamellar bending and the lamellar breakage. The transmission electron microscopy image for the 10% deformed sample shows the presence of dislocation network and dislocation movement activity in the interface. Therefore, we can see that the deformation mechanism is the dislocation interaction and the dislocation in the interface. Also, in FCC phase, we can see that the large lattice distortion with the localized fluctuation of the interplanar spacing can be observed. Further, the transmission electron microscopy of the highly deformed, that is a 55% 0.5 SCR, shows the high the density of dislocation in the FCC phase and the presence of dislocation tangles, lamellae bending, lamellae breakage, dislocation pileup, and the highly distorted interface can be seen. And when we measure the dislocation density, we see that the dislocation density in case of FCC phase is increases at to a magnitude order magnitude when we deform the sample up to 55%. Therefore, from this we can conclude that the strain sensitivity and the activation volume remain in the range of 0.0070 to 0.0082 and 24 to and activation volume in the range of 24 to 8 B cube to 43.7 B cube. In this range, it shows that the deformation mechanism is dislocation mediated. Also, the TM study along with the strain rate sensitivity and activation volume shows that with the addition of the increase of the cold working and deformation mechanism is highly influenced by the large lattice distortion with localized fluctuation. The dislocation activity at the interface and the dislocation cutting with false dislocation at the lamellae and high dislocation density pile up by formation of deformation band can be seen. The strain rate sensitivity and activation volume measured from the strain rate jump test confirm the dislocation mediated plastic flow for the entire range of the average eutectic lamellae. Also, the reduction in the activation volume in suction caster dot occur because of the reduction of the dislocation mean free path with the decrease of the average eutectic lamellae. The smaller the average eutectic lamellae, the greater area for the lamellar interface that act as a key hindrance for the motion of the dislocation. So from the other chapter, we have summarized that we have successfully prepared two new series of eutectic high-entropy alloys, and with the addition of niobium and tantalum, the microstructure vary from hypoeutectic to eutectic and hypereutectic. Also, the average eutectic lamellae thickness is lowest in case of suction casted rod, which results in the increase in the yield strength. The local hardness increases from the center to the periphery on the cross-sectional plan, which is due to, in the present case, we can see that which is due to the refinement of the average eutectic lamellae thickness. We have assessed and predicted the phases based on various thermo-physical and electronic parameter, and we see that the phases become stable when the electronegativity parameter is 5.5% and the mixing enthalpy is in the range of -18 to -6. Valence electron concentration remains in the range of 6 to 8.5 with atomic size differences greater than 3%. Two artificial neural network has been proposed for the phase prediction, that is SCO and FCBOA, which shows high accuracy for the phase prediction for the deployment dataset. A high temperature deformation shows that in the intermediate temperature, the strain hardening plays dominant role, whereas in case of at higher temperature, the dynamic recrystallization, that is the dynamic softening plays major role. Also, the various coarsening mechanism can be seen, that is the dimensional migration, cylindrization, edge spheroidization, and boundary splitting. The strain rate sensitivity and activation volume remains in the range of 0.0070 and 0.0082 and 24.8 BQ to 43.7 BQ, which suggests that the deformation is dislocation mediated. The TEM image shows that the large lattice distortion with localized fluctuation. Also, the strain sensitivity and activation values for the eutectic high-entropyalloys measured. So the strain rate jump test confirms the dislocation mediated plastic flow for the entire range of average eutectic lamellae thickness. So these are the work can be done in the future. That is, hot deformation behavior can be studied for the various strain rate range. Mechanical behavior of the annual specimen can be studied, and the various thermomechanical processing can be performed to further play with the various or the improvement of the mechanical and various parameters, various properties. These are my list of publications. These are the list of conferences I have attended. I acknowledge my supervisor and doctoral scrutiny committee members and PhD thesis examiner for giving his valuable time and suggestion for the improvement of the thesis, and my lab mates and all colleagues. Thanks for your kind attention.
Okay, thank you, Barnasree. Very good, enthusiastic presentation. Okay. And then I request Professor Bhattacharya. Dr. Bhattacharya, you please, now the floor is yours. You have to make some comments or questions, whatever you want to do to Barnasree. Dr. Bhattacharya, please.
Yeah, thanks for your presentation. Okay. So at the outset, I will say that actually eutectic high entropy alloys, if you look at, it is one of the most studied high entropy alloys.
Yes, sir.
Group. Okay, and one of the most known high entropy alloys, possibly one of the most extensively investigated, including us, is the aluminum, cobalt, chromium, iron, nickel 2.1. You may be aware. And the enthusiasm in high entropy alloy comes from this particular mixture of FCC plus B2, which is a hard phase and a soft ductile matrix. Okay, so that is the reason which will immediately caught the attention of the community. Now, if we extend it to other high entropy alloys, this is a general comment. Like for instance, niobium or other, you can see immediately the other compositions where it forms into is basically contains a lot of lattice phase. The problem with is that in aluminum, cobalt, chromium, iron, nickel 2.1, you get a lot of tensile ductility. But none of the other high entropy alloys, which including what you have prepared, they do not have a tensile ductility. You can do it in compression, that's why the reason you do it in compression. Okay, so most of the high entropy alloys, apart from which does not have a FCC plus B2, it does not have a tensile ductility. So we have to make a distinction when we talk about mechanical properties. We have to make a distinction between a tensile ductility and a compressive ductility. Okay, so that remains a challenge. I hope you get my point, what I am trying to say.
In 2016, when we started working, the alloy compositions you have talked about, aluminum, cobalt, chromium, iron, nickel 2.1, which is proposed in 2004 by 14 by Lu et al. That is the first term that eutectic high entropy alloys. So therefore, in 2016, we thought of propose a new class of eutectic high entropy alloys. Therefore, we have prepared this alloy system, and and we have not performed tensile tests because our samples are very small. So therefore, we are getting problem while gripping.
So for your eutectic alloy, which is FCC plus BCC, FCC plus lattice phase, particularly, did you carry out your tensile test?
No, sir. Due to the limitation of the sample size and the gripping problem, we were not able to do the tensile test actually. Therefore, we have moved for the 3-point band test.
Yeah. So you can basically see it has very limited ductility, and it is not uncommon to see because you have a lot of lattice phase, which is not very ductile. So that is what I wanted to say, that this particular, when we talk about eutectic high entropy alloy, a particular this combination FCC plus B2 somehow is possibly the most attractive compared to any other combination of this. At least this is my view, that other combination or other phase constituents, it do not give that kind of advantage which the aluminum, cobalt, chromium, iron, nickel 2.1 enjoys. Okay. So this is one comment, but this is something not to do with that, but to give you a broader possibly perspective on this. Now the second comment is that and later you can go through my comments, is that in general lattice phase is known to be a brittle phase.
Yes, sir.
Okay. So you do not expect a lot of tensile ductility. What is typically for your hyper eutectic composition? Have you determined the fraction?
Yes, sir. For hyper eutectic, we have measured. And we have seen that for the augmented ingot, it varies in the range of 15 to almost 28, something like that, 20 volume percent.
Yeah. So when our experience with that is that, of course, it was not a cobalt, chromium, iron, nickel alloy, But it was basically a cobalt chromium. We took the base of the cobalt chromium iron nickel 2.1 and niobium, and I have referred to some paper probably there. So with such an, if your lattice space content is of that extent, you cannot have a tensile ductility on these alloys. Okay, so that is what I think. In general, you can of course you can do hot deformation studies and etc. But this is a general comment on the thesis that tensile ductility, which is a challenge, but that probably cannot be achieved. Compressive ductility is not a problem because even in the brittle phase you can have a compressive ductility, and even the high temperature ductility is not a present. It is not a problem, but tensile ductility at the ambient temperature is definitely more challenging with such microstructure.
As you talked about that extension of abstract, we have to follow some guideline while preparing thesis, and which
fair enough, no problem. Yeah.
And now, which we have talked about right now, that is the problem related to tensile ductility, which I have addressed in my literature review. Then one mistake was there. I write there high tensile strength rather than ill strength, that I have corrected in my literature section. And also the thermomechanical processing, which we have talked about, and maybe that by that also we may increase our property or enhance our property. With that, I have added in my future work section.
Okay, all right. Please go ahead.
So basically, we have done AFM to see if there are any presence of crack or not. So that may show some different result or something like that. So therefore, we have done AFM to see if there are any pileup or any crack is present there or not. So that line I have added in my thesis in the experimental procedure. And
so
the lubricant.
Pileup means the pileup of dislocations, right?
Yes, sir. Pileup of materials. Sorry, sir.
Okay, pileup of materials.
Yes. Okay. Pileup of materials, and if there are any cracks around the indentation impression. And sir, for
indentation, so indentation you have taken in the FCC phase, or you have taken in at the interface of the FCC and Lavis?
Sir, I have taken on the Lavis phase and on the matrix.
Okay, so independently.
Yes, sir, independently. Yes, sir.
Okay, so that means you get the mechanical properties behavior for the two independent phases, right?
So two independent phases means, yes, sir. One is for eutectic matrix and one is for our Lavis phase.
So how much times roughly it will be high for this?
Sir, from here we can see that at 0, that is 0% cold work, and without any deformation, we can see that is this star are suction casted rod that is approximate 3 GPa, 8 GPa. And in dendrite, it is around 8.6 or something like that GPA.
But then it is not so much difference, right?
Sir, I have changed the title, compressive, that is, and modified in my thesis for comment A. Mention the compressive stress strength rather than simple strength.
Okay.
And then this comparison is also already made in that yield strength versus inverse, that average eutectic lamellar thickness for fully eutectic. Therefore, we have not compared with hyper and hypo. We have compared for fully eutectic microstructure. And then the idea of Lavis phase, yes, sir, I have already mentioned it in my thesis.
Okay, fine. Because I was a little bit confused because it was not explicitly mentioned that whether it's a compressive or this. So now you have done it. Okay, fine.
So for the phase prediction through by ANN, artificial neural network, we exclusively collected data for arc melted prepared alloys prepared by arc melting only. We have not considered alloys processing through any other method. Yes, sir, it is written there. In my thesis, it is written.
Okay, all right then.
Another issue data is training is sufficient. So that is why we have collected from all the possible literature, we have collected the data, and we have got a good prediction percentage of 92%.
Okay, all right. Yeah.
And, yes, sir. And yes, so we have predicted for Young's modulus, and we got very high accuracy of 96%. But for as per your suggestion, chapter 7, strain rate jump test carried out at room temperature, the experimental alloys all show a very small m value consistent with expectations of room temperature deformation. Whereas it may be out that test, if carried out at high temperature, would be more useful, particularly in context of hot deformation. Yes, so we have as per your suggestions, we have taken this as our future work.
Okay. All
Yeah.
right. So congratulations, Dr. Barnasree Chanda. So I think you have done it. So it was. I understand it was quite a, probably your effort for last 5-6 years, and I always say that. There are a lot of surprises when you work on high entropy alloys and etc. It always throws you more surprises than you expect. So I think you have chosen a very interesting alloy system, and you have worked meticulously, and you have put a lot of effort. So I congratulate you on your achievements, and I wish the best for your future endeavor. And your
I request all the other DSC member to switch on the camera so that I can take a picture actually.
Okay, Barnasree, very good work and keep it up.
Professor Jijira, please switch on the camera.
I have done it.
Okay.
And keep it up. Okay. Okay, that is what I can say. Very good work and very hard work also. Basically, you have done a very laborious effort you have given, and you have got the results also. Very good. Dr. Barnasree Chandra. So we can call you as Dr. Barnasree Chandra. No more Barnasree. Okay. Okay, congratulations.
Thank you, sir.
Indrani's mic is off. Professor Gautam Chakraborty's
Congratulations, Barnasree.
Thank you, ma'am.
This is the best part of this defense seminar, where you get to hear this for the first time. This is always special.
Fields also.
Yes.
But throughout the life, don't work on high entropy alloys. So there are many other things. So widen your research areas.
Yeah, during I think her master's degree she worked on wood actually. So fracture and bending of wood actually. So and then this is high entropy. So okay, congratulations, Barnasree. Congratulations from our side. So you did some.
Congratulations to Professor Das also.
Thank you.
Yeah.
Yes,
nothing.
Definitely.
Das is getting a few days back on. So by 1 month, Jayanta, you just how many students graduated? I think 2, na? This is
Two.
second.
Two.
Anand and this.
Yes.
In 1 week's time, I guess.
Yeah, in Vastly. And how many are there in pipeline?
No, I don't want to stop anybody's defense, or I don't want to hold anybody. If you have written the thesis, submit it and go away. That's all.
And if you can make 4 chapters, that's all. I have seen Jayanta's thing. There will be 4 chapters. 1, 2, 3, 4, and then it is coming to an end. I understand now.
Okay. So and anyway,
What is the magic number, right?
I really thank.
You have to write 4 chapters. How long it takes?
But the students have done very good work.
Right, lot of extensive work. That's true.
I really thank Professor Bhattacharjee to be a part of this committee and to take all the pains for reading thesis and evaluating and extending help for its betterment, and all the DSC members throughout this time of 5 years, and Professor Gigi Rai for his help on every aspects actually. So with this, I really thank everybody, and Professor Gautam Chakraborty, Professor Indrani Sen, Professor Chandrasekhar Tiwari for all the help you have done actually.